Welcome back to the deep dive. We're going to be doing a deep dive today into the world of large language models.
Okay.
Specifically DeepSeek V3.
Sounds good.
It's a 671 billion parameter model making waves for its unique approach to efficiency and performance.
Right.
And you shared an academic paper detailing its architecture.
Yes.
And as a machine learning expert, you are looking to understand how DeepSeek V3 achieves both high performance and economical training.
Yeah, that's right. Oh, hey there. What's up?
Can we focus on the MLA, the details of the MLA and how it works?
Absolutely. That's a great idea.
Yeah, we can definitely dive deeper into the multi-head latent attention, or MLA.
So you're curious about the nuts and bolts of MLA.
Well, let's unpack this.
We mentioned that one of the keys to DeepSeek V3's efficiency is its mixture of experts, or mole architecture.
Right, where only a fraction of the parameters are activated for each token.
And the DeepSeek V3 takes us a step further with MLA and DeepSeek Mo.
That's right. So let's really focus on MLA right now.
Okay, so in real-time applications, speed is critical.
It is.
And the key value cache needed during inference can be a major bottleneck.
Exactly. That's where MLA comes in.
Okay, so the traditional attention mechanism requires storing a lot of information about previous tokens.
Yeah.
Which, as you can imagine, becomes a problem with long sequences of text.
Right, but MLA cleverly compresses this information.
Okay, just significantly reducing the cache life.
And making inference much faster.
So it's like it's taking a bulky encyclopedia and condensing it down to just the key points.
That's a great analogy. It retains the essential information without the unnecessary weight.
Yeah, so it's really useful for real-time applications.
Yes. Now let's talk about how it actually works.
Okay, so how does MLA achieve this compression?
Well, it uses a low-rank joint compression for attention keys and values.
Okay, so it's compressing the keys and values, but what does that mean exactly?
So let's get a little technical.
Okay.
The MLA mechanism takes an input hidden representation, which then projects into query, key, and value vectors.
Okay.
Now, here's where it gets interesting. MLA decouples the query into two parts.
Okay, two parts.
Yes, one part is used for the content, and the other part is used for positional information using something called ROPE.
ROPE, that sounds very techy.
It stands for Rotary Position Embeddings, and it helps the model understand the position of the tokens in the sequence.
Okay.
Then, the keys and values are compressed into a lower dimensional latent space.
So it's like they're shrinking the data, which saves on memory.
Precisely.
So it's like the most important info is saved, but the unnecessary bulk is discarded.
Yeah, and this compressed representation allows for a much smaller KV cache during inference.
So that speeds things up.
Exactly.
And it also uses multi-head processing.
Yes, just like traditional attention, MLA employs multiple heads. Oh, go for it.
So why there are two latent space and one hidden input?
That's a great observation. Yes, you're right. There are actually two latent spaces.
Okay, so we're talking about a content latent space and a key value latent space.
Exactly. And these latent spaces are processed through what we call ROPE, or Rotary Position Embeddings.
Okay, so that ROPE is how they get the positional information.
Yes, it's applied to both the content and key value latent spaces, as you pointed out.
So it takes this compressed representation, processes it, and then combines it all back together.
Yes, and the caching optimization further reduces overhead during sequential processing.
Okay, so this is how MLA speeds things up.
Exactly. It's a clever way to achieve efficient attention without sacrificing performance.
Okay, that's a pretty neat trick, but you know what?
What's that?
Let's move on to DeepSeek Mo. How does that differ from traditional Mo models?
Okay, DeepSeek Mo uses...
Oh, back to our listener. What's up?
Can we talk more? The hidden space, the key from the hidden space, what's that?
Absolutely. I see what you're getting at. The hidden space is really interesting.
Yeah, you're asking about the hidden space, the latent space that we were just talking about.
Right. You're curious about what's going on within those latent spaces, that cave.
Yeah, it's not just about the number of latent spaces, but what happens there. That's cool.
Exactly. There are indeed two distinct latent spaces within the MLA, one for content and one for key values.
It's like having two separate storage units for information.
And these latent spaces, as we've discussed, undergo ROPE operations.
Right, the rotary positional embedding.
Which embed positional information into the attention mechanism. That's very important for them.
So to recap, the query is split, and the keys and values are also compressed.
Yes, and these are put into the two separate latent spaces, one for content and one for key value pairs.
And these latent spaces are really important for efficiency, and all that is part of the MLA.
Exactly. Now let's talk about these operations in a little more detail within the cave, as you put it.
Okay, so how does MLA actually perform these latent space transformations?
Well, the input undergoes parallel processing for both the content and key value representations.
Okay, so it's like it has two paths within that cave.
Yes, one for each latent space.
And within those spaces, the information is processed using rope.
That's right. This ensures that the model retains the positional information as they go through the cave.
So the model knows which part of the text is which as it is inside that cave.
Exactly. And this processing is done before the next stage of concatenation.
Okay, what is being concatenated as it goes through the hidden space cave?
The mechanism performs two major concatenation operations. The query representations are concatenated, and the key representations are also concatenated.
So it's like bringing all the important pieces together within that hidden space cave.
Yes, and these concatenations help combine the content with the positional information.
And these concatenated representations are then used for attention calculation, right?
Correct. And because of the initial compression, it is much faster through that cave that you mentioned.
So MLA significantly cuts down on computational costs inside and outside of that hidden cave.
Exactly. It optimizes the attention mechanism for large models like DeepSeek V3.
That's a great question. Now, after we've gone through the cave, let's move on to DeepSeek Mo.
Okay, DeepSeek Mo.
That's right. I see what you're getting at.
Yes, there are indeed two distinct latent spaces within the MLA.
One for content and one for key values.
Exactly. And this separation is really key to how it works.
It's like having two separate storage units for information.
And these latent spaces, as we've discussed, undergo rope operations,
Right, the rotary positional embeddings.
which embed positional information into the attention mechanism.
So to recap, the query is split, and the keys and values are also compressed.
Yes, and these are put into the two separate latent spaces, one for content and one for key value pairs.
And these latent spaces are really important for efficiency, and all that is part of the MLA.
Exactly. Now let's talk about these operations in a little more detail.
Okay, so how does MLA actually perform these latent space transformations?
Well, the input undergoes parallel processing for both the content and key value representations.
Okay, so it's like it has two paths.
Yes, one for each latent space.
And within those spaces, the information is processed using rope.
That's right. This ensures that the model retains the positional information.
Right, and then to enhance the efficiency, it uses shared experts.
Okay, so experts that can be used across multiple tasks.
Yeah, so that avoids redundancy and makes the system even more streamlined.
Yeah, it's like having a team where people have specialties but can also do other things.
Yeah, that's a really smart approach.
Yeah, but with so many specialized experts, how do they ensure that none become overloaded?
Yeah, while others sit idle.
That's where their innovative auxiliary loss-free load balancing comes in.
This is where things get really interesting.
Right.
So how do they do that?
Traditional MI models use an auxiliary loss function during training
Okay.
to encourage even expert usage, but this can actually hurt performance.
Yeah, it's like trying to force everyone to use the same checkout line at the grocery store.
Exactly, even if some are moving faster than others.
Right, it just creates unnecessary delays.
Yeah, so DeepSeek V3 avoids this by dynamically adjusting a bias term
Okay.
for each expert based on its load. Okay, so if an expert is getting too many requests,
The system makes it slightly less appealing to the routing mechanism.
gotcha, diverting some of the traffic to less busy experts.
Okay, so it uses all this to efficiently handle long sequences.
Yes, by reducing the size of the KV cache needed for inference.
Okay, so it's all about keeping performance high while reducing overhead.
Right, it's a very clever approach to addressing a critical bottleneck.
Absolutely. Now, we should also cover how DeepSeek V3 handles its load balancing.
Yes, we definitely should. This is also a really important piece to the puzzle.
We can touch on that next.
Sounds good. Well, I think that gives you a great overview of MLA and its latent space.
Yes, thanks for diving into all the details with us. We'll be back next time with more deep dives.
Yes, it's like a traffic management system for the experts.
Yeah, constantly monitoring the flow and making adjustments.
To avoid bottlenecks.
And that avoids the performance hit of the auxiliary loss.
That's right. And
Oh, go for it.
Then we can talk about MTP, how MTP modules share their embedding and output head.
Absolutely. It's a great question.
yeah, let's talk about how the MTP modules share resources.
So you're curious about the nitty-gritty of the MTP implementation.
Yeah, let's unpack this.
So we mentioned that DeepSeek V3 uses MTP for multi-token prediction.
Right, predicting multiple tokens instead of just one.
And this is where it gets really interesting.
Yeah, you're interested in how the MTP modules are set up and how they share their resources.
Okay, so each MTP module includes a shared embedding layer.
Yeah, and a shared output head.
Okay, so they use the same embedding and output head as the main model.
Exactly. So it's like they're all drawing from the same pool of knowledge.
Yeah, and that saves on computational costs.
Yes, now it uses its own transformer block.
Okay, so it's not sharing the same transformer block as the main model.
Correct. Each MTP module has its own transformer block for processing.
Okay, so that's how they keep the predictions distinct for each token.
Yeah, and to combine the information, they use linear projections and concatenation.
Okay, so it's like taking pieces from multiple places to build the complete picture.
Yes, and all the MTP modules work together in parallel.
But they share their embedding layers and output heads, right?
Yes, which is key to the efficiency of this design.
Okay, so it's like a system of interconnected parts that all rely on each other.
Right, and this efficient sharing of resources allows for faster training and better performance.
Okay, that's a pretty neat trick, you know what?
What's that?
Let's move on to a big picture view. How does this model handle load balancing? How are those experts chosen?
Yeah, we can definitely talk about that.
Okay, now let's dive into DeepSeek V3's load balancing strategy.
Sounds good. Okay, so DeepSeek V3 uses what they call multi-token prediction. Oh, yeah,
Can we talk more about the detail of the MTP?
Absolutely. I'm glad you're interested in diving deeper into MTP.
Yeah, we can definitely elaborate on the multi-token prediction.
So we touched on it, but let's really unpack the details of MTP.
Right, we were talking about the shared embedding layer and output head.
Yeah, and that each MTP module has its own transformer block.
Exactly, but there's more to it than that, so let's go into it.
Okay, so let's talk about the sequential nature of the MTP modules.
Yes, unlike some models, DeepSeek V3 predicts additional tokens sequentially.
So it's not just predicting all the tokens at once.
Correct. Each module builds upon the output of the previous module.
Okay, so it's a chain of predictions, each one dependent on the last.
Yes, and it maintains the causal chain for each prediction depth.
Okay, so it's not breaking the causal flow.
Exactly, which is important to ensure the overall context is correct.
So the MTP modules don't just work independently.
That's right, they're interconnected.
And this chain of prediction contributes to greater training efficiency.
And allows for a more nuanced understanding of text.
Now, you're also interested in how the modules share their embeddings.
Right. As you know, the shared embedding layer maps tokens to their vector representations.
Okay, so each token is converted into a vector.
Yes, and this mapping is shared across all MTP modules.
Okay, so that helps maintain consistency across the predictions.
Exactly, and the shared output head takes the final hidden states of the tokens
Okay.
and generates the probability distribution for the next tokens.
So it's like they all have access to the same information pool.
Right, and this is really crucial for memory and computational efficiency.
Okay, so it's not using a bunch of different embedding layers and heads.
Exactly, and the
So there are how many MTP modules? Then there are the same size output tokens. Is that right?
That's a great question. You're asking about the number of MTP modules, whether they're all the same size.
Right, and I think you're also wondering whether all the modules handle the same amount of data.
Well, from the paper, DeepSeek's V3 uses a multi-token prediction depth of 1.
That means there's the main model, and then just one MTP module that predicts one additional token.
So each token predicts the next one, and then one more after that, using that MTP module.
Yeah, and the MTP module does have the same shared embedding layer and output head as the main model. Okay, that's a great question.
Yeah, you're asking about how many MTP modules there are and if they're all the same size?
Well, according to the DeepSeek V3 paper, there are a varying number of MTP modules.
Okay, so it's not fixed at one particular amount?
That's right, the number of modules is dynamically adjusted based on the prediction depth.
Okay, so they can be scaled as needed. So they're sharing those resources, but the transformer blocks of the main model and MTP module are separate.
Correct. Each prediction depth has its own transformer block.
Okay, so there is only one MTP module, but it's a powerful one that gets used for each token, and they share some resources.
Exactly. And while the MTP module shares some components with the main model, they're not exactly the same size.
Okay, that's a really good point.
Now, I think we should also talk about how they combine all this information to make predictions. Exactly. DeepSeek V3 uses multiple MTP modules to predict several additional tokens, one after another.
Okay, and you asked if they're all the same size, right?
Yes, and the answer is that they're not necessarily the same size.
So the transformer blocks within the MTP modules can vary.
Yes, they can, to adjust to the varying needs of each depth of prediction.
Okay, so it's not just a set of identical modules.
Exactly. It's a more flexible system that adapts to the prediction task.
So it's like a custom tool for each stage of the prediction process.
Yes, and this dynamic scaling helps optimize the performance and efficiency of the model.
Okay, and you also asked about the food.
I think that was just a little bit of a slip up.
Yeah, I think so too. Okay, so how do they integrate the information and make predictions?
Yes, and this design also allows for speculative decoding, which is really cool.
Okay, so it's not just for training, but for inference too.
Correct. The MTP modules can be repurposed in inference for speed.
So MTP is used to generate possible future tokens.
Yes, and then it picks the best token from the possibilities. But yeah, they are not all the same size, as you correctly asked.
So the transformer block sizes in the MTP modules can vary.
Yes, to optimize performance, so it's very flexible.
And this flexibility contributes to the efficiency, as we've been talking about.
Yes, it's all part of DeepSeek V3's innovative approach to multi-token prediction.
Okay, so now we have gone into the cave, covered the MTP module sharing, and discussed their varying number and size. Okay, so it generates text more quickly.
Yes, it saves time by not having to calculate each token from scratch.
Okay, now let's shift to a bigger picture view.
Yes, we can talk about how the experts are chosen for each task.
That's right. Now let's dive into DeepSeek V3's load balancing strategy.
Sounds good. Okay, so DeepSeek V3 uses what we were just talking about, the MTP. Yes, we should probably move on to the bigger picture now.
Okay, so now let's discuss how this model handles its load balancing.
Yes, and how those experts are chosen.
Okay, now let's dive into DeepSeek V3's load balancing strategy.
Sounds good. Okay, so DeepSeek V3 uses what they call multi-token prediction, or MTP.
We've just discussed how MTP works, so now let's talk about the load balancing, right? Yes, we were just talking about that and how it shares resources.
And you were curious about how it shares resources. We got into that.
That's right. So instead of predicting just the next token,
Right, it predicts multiple future tokens at once, as we just discussed.
doesn't that increase the complexity though?
It might seem that way, but it offers several advantages.
Okay, imagine planning a route if you only consider the next turn. Yeah, you might miss a more efficient path. Okay, looking ahead and planning multiple turns allows you to choose the optimal route.
Yes, DeepSeek V3 uses an innovative approach called auxiliary loss-free load balancing.
So it doesn't rely on a separate loss function for balancing
Exactly. Traditional MoE models use an auxiliary loss function during training.
to encourage even expert usage, right?
But this can actually hurt performance, as we mentioned earlier.
Yeah, it's like trying to force everyone to use the same checkout line at the grocery store. Okay, so by predicting multiple tokens, the model gets a better grasp of the context.
Yes, and it can generate more coherent and accurate responses.
It's like the model is pre-planning its representations, like I mentioned earlier.
Yes, for better future predictions.
Okay, and this leads to denser training signals.
And improved data efficiency. Yes, so instead, DeepSeek V3 dynamically adjusts a bias term for each expert.
Okay, based on its load.
Right, if an expert is getting too many requests, the system makes it less appealing.
And that diverts traffic to less busy experts,
Yeah, like a traffic management system for the experts.
constantly monitoring the flow and making adjustments. So what else can MTP do?
The MTP modules used during training can either be discarded during normal inference
Okay,
or cleverly repurposed for something called speculative decoding.
okay, speculative decoding, what's that?
Instead of just predicting the next token, the model also predicts potential alternatives that might follow.
Oh, wow.
So it can generate text faster because it's already considered multiple possibilities.
Like having a backup plan ready to go.
Yes, so the model doesn't have to pause and recalculate every time.
Okay, that makes sense.
Yeah, now speaking of efficiency, to avoid bottlenecks.
And that avoids the performance hit of the auxiliary loss.
That's right, and they also include a complementary sequence-wise balance loss.
Yeah, to prevent extreme imbalances within individual sequences.
And by limiting each token to a maximum of 4 nodes, they reduce network communication.
Okay, so that helps streamline things as well. Right.
Let's talk about how DeepSeek V3 manages the computational demands of training.
And I know you are particularly interested in cost optimization and how they're doing things economically.
Yes,
And this model does some amazing things in that area.
it does. Yes, the average is 3.2 experts chosen per token.
Which is a nice balance to reduce the overhead.
Exactly. So it is a very efficient and effective method.
Yeah, it's a really smart approach to making a model this complex work so well.
Yes, and they also achieve expert specialization through this method.
Okay, so that means different experts are activated in different domains. So what are they?
DeepSeek V3 utilizes an FP8 mixed precision training framework,
Okay.
a significant breakthrough for a model of this scale.
Remind me what FP8 is again?
Sure, it's 8-bit floating point.
Okay.
And it represents numbers using fewer bits than traditional formats.
Okay, so this translates to less memory and faster computation.
Exactly. It's like compressing a large image file, but you still get the essence of the image.
It just takes up less space.
Right. Exactly. So each expert isn't just generically activated, but in specific domains.
So it's finely tuned and ready for action.
Yes. Now, this batch-wise approach is really clever.
Yes, I agree. This dynamic approaching to load balancing is fascinating. It's all about efficiency and balance.
Yes, it's all part of DeepSeek V3's commitment to both performance and resource utilization.
Absolutely. Now, we've covered a lot today. It's really interesting. But wouldn't using fewer bits potentially impact the accuracy?
That's a valid concern, and it's something they addressed carefully.
Okay.
They implemented a number of techniques to mitigate any potential accuracy loss.
Including fine-grained quantization.
Yes, it allows for precise control over how numbers are represented in FP8. Yeah, from the multi-head latent attention to DeepSeek Mo and the load balancing.
Yeah, this DeepSeek V3 model is a very sophisticated system.
And it's a great example of how innovation is pushing the boundaries of AR.
Yes, it's been a fun deep dive today.
Yes, I think that gives you a solid overview of DeepSeek V3.
Absolutely. Thanks for exploring it with us.
Yes, thank you. And that's it for today's deep dive.
We'll be back with another one soon. So they're striking a balance between using